So we saw that the norm of a linear operator is given as norm L is equal to sup over x belonging to domain of L, x not equal to 0, norm Lx by norm x. Right? And now the idea is that for a matrix norm, right? So when we consider the special case of a matrix, when we consider matrix A, okay, then its P norm is given by norm AP is equal to sup over sup x not equal to 0, sup of x not equal to 0, and norm AX P norm by norm x. That is also P norm. Now the idea is that, right, now such a norm, right, I mean we've seen other kinds of norm, we've seen Frobenius and all of that, right, and okay, that norm and which incidentally was also a matrix norm. Now, if you compare that matrix norm with this norm, right, the norm that comes via a form like this is called an induced norm, okay, or it's called a vector induced norm, because it's actually induced by the norm of this vector, norm AXP by norm XP, and that gives you a Pth norm. For example, if P is equal to 2, right, for P equal to 2, you get what is called the spectral norm of A. For P is equal to 2, you get the spectral norm of A, which is what is going to be of interest to us, because the spectral norm has certain special properties that can actually that can help us understand the numerical stability of a matrix, and therefore the spectral norm is given as norm 2 is equal to sup x not equal to 0, and then norm AX, even 2 norm of AX, the vector AX, and 2 norm of the vector X. Now compare it with if you compare this with the entry-wise norm, the other norm. Okay, now this is anyway, right, just as an aside. Okay, for those of you who might be just interested in knowing, this is a vector-induced norm, right? Whereas on the other hand, okay, if you have entry-wise norm, okay, which is what we have seen earlier when we did transforms and all, image transforms and all, we had what are called entry-wise matrix norm, and that norm was actually given by norm AP is equal to, if you recollect, we had it like summation over all entries of A and Ij, and then magnitude Aij P the whole power 1 by P. Okay, this is called an entry-wise norm, and P equal to 2 was actually a Frobenius norm, right? P equal to 2 gave us the Frobenius norm of A, right? So which we denoted as norm A, and then we put F here. Okay, that is a Frobenius norm. Now P equal to 2. Now for P equal to 2 here, you get this form. Okay, and this is called a spectral norm. Okay, so a matrix has various different norms. There's also something called the Shaton norm and so on, which is in terms of the singular values and so on. Okay, but right now our focus is on the spectral norm. It's called the spectral norm because it eventually turns out that this norm can be expressed in terms of the eigenvalues of this matrix. Therefore, it's called the spectral norm. Okay, we'll see all of that as we move along. Now let's go back to this expression. Norm A, the spectral norm, is equal to sup over x not equal to 0. Now I can write norm AX by norm x as root of x transpose A transpose AX upon x transpose x. Right? Turns out that it is the same as. Now there is a matrix inequality, right? That says there is a matrix inequality result, which says that lambda x transpose x, a scalar, times lambda min of A transpose A. Right? So this is the minimum eigenvalue of A transpose A is less than or equal to x transpose A transpose AX, and this in turn is less than or equal to x transpose x into lambda max of A transpose A. Okay, where x is a vector and so on. Okay, now Now, it is this inequality that we'll try to use here when we want to compute the spectral norm of A, but then we can actually show this result. Okay, we can actually show this inequality, and to show that, let's kind of look at what is called the Rayleigh quotient. The Rayleigh quotient of a matrix. Okay, now Rayleigh quotient is given as R of X is equal to X transpose A transpose AX upon X transpose X, right? In fact, the term sitting here is in fact this is the Rayleigh quotient. Now, A transpose A is actually a normal matrix, correct? Normal matrix. Okay, now what is a normal matrix? We have already seen while doing image transforms. B is a normal matrix if B transpose B, B transpose is equal to B transpose B. And of course, when B is symmetric, if B is symmetric, this is automatically obeyed. A transpose A is a symmetric matrix, and therefore it does obey this, and therefore it's a normal matrix. And what is so special about a normal matrix? A normal matrix is unitarily diagonalizable, and hence is unitarily diagonalizable. This is again something that we have seen when we did image transforms. It's unitarily diagonalizable. Okay, unitarily diagonalizable. Okay, now what does that mean? That means that A transpose A can be written in terms of a unitary transform as U transpose diagonal U. That is, diagonal contains eigenvalues of, remember, A transpose A, not A. Okay, eigenvalues of A transpose A. And because of the fact that A transpose A is symmetric, therefore the eigenvalues are real and greater than or equal to 0. Values are real and greater than or equal to 0, clearly, right? Because of the fact that this is a symmetric matrix. Now, what this means is that I can rewrite X transpose AX as X transpose, then I replace A transpose A by U transpose diagonal U, and then I get back to X. Let's say Y be equal to UX. Okay, therefore X transpose AX when written in terms of the unitary transform becomes Y transpose diagonal Y. Okay. Similarly, X transpose X can then be written as X transpose UY, because U transpose U is identity, it's a unitary transform. Okay, we remember, right? Remember, this is a unitary transform. This is a unitary matrix. Okay, that is U transpose U is equal to U transpose is equal to identity, right? Now, and therefore, right, this then becomes equal to Y transpose Y if I simply put substitute for, oh sorry, this is X. If substitute for UX as Y, then I get Y transpose Y. Therefore, X transpose AX upon X transpose X becomes equal to Y transpose diagonal Y by Y transpose Y. But if you call the eigenvalues, right, if these eigenvalues are lambda 1, lambda 2, all the way up to lambda n, then what we have is this becomes equal to lambda 1 y1 square plus lambda 2 y2 square all the way up to plus lambda n yn square upon y1 square plus y2 square plus yn square. Okay, now this ratio clearly lambda 1 y1 square plus lambda 2 y2 square plus lambda n yn square upon y1 square. Okay, now this, right, this clearly is less than or equal to divided by, let's divide it by y1 square plus y2 square plus yn square. This ratio clearly, let me write this clearly on top because I would like to use something on the left. So clearly, this should be less than or equal to lambda max of A transpose A, because see, each is an eigenvalue of A transpose A. Okay, this sum, okay, this ratio in fact should be less than or equal to, and should be greater than or equal to lambda min of A transpose A. Right? It's obvious, because it's y1 square over y2 square, because you can take lambda maxes. If you pull lambda max out, then of course, right, actually you don't need the rest are all less than lambda max, and therefore this should be less than or equal to lambda max of A transpose A. Similarly, if you try to pull lambda min, okay, then the rest are all greater than lambda min, therefore this ratio should be greater than or equal to lambda min of A transpose A. Now, right, this ratio is nothing but, as we saw earlier, this can be rewritten as X transpose AX. This is nothing but X transpose X, right? Written in terms of X. And therefore, right, that result that I wrote down follows: X transpose X into lambda min A transpose A is less than or equal to, okay, now X transpose AX, because this X transpose X goes and multiplies on the left and the right, is equal to less than or equal to X transpose X into lambda max of A transpose A. Okay, now right, this is an upper bound. Now this upper bound can even be met. Okay, the upper bound is met when, because we are interested in the supremum, right? So the upper bound is met. Okay, now yeah, the same, right? We can also write this as okay, we can just divide this whole thing by X transpose X, and therefore, right, we can write this as upon X transpose X. Okay, so this goes away from here. Oops. Okay, let me remove this underline thing, and then let me remove this from here. Less than or equal to lambda max. Okay. Therefore, right. So it's kind of back to the same equation here, and this is the ratio for whose sup we are trying to find out, and this will equal this. Okay, when X. Okay, this is valid for all X. Right. This is valid for all X. For all X. When X is chosen to be the eigenvalue, it's chosen to be the eigenvector corresponding to, chosen to be the eigenvector corresponding to the eigenvalue lambda max of A transpose A, if you choose, because it's valid for all X. Therefore, let me choose X to be the eigenvector corresponding to the maximum eigenvalue, that is lambda max of A transpose A. Then X transpose A transpose AX becomes equal to X transpose, because A transpose AX, okay, becomes then equal to lambda max of A transpose A into X, and this X transpose, which is equal to X transpose X into lambda max of A transpose A, and this X transpose X will knock off this X transpose X, and you'll get lambda max of A transpose A, right, as an equality, correct? And therefore now the spectral norm of A is given as root of lambda max of A transpose A. And in terms of singular values, we know that the positive square root of the eigenvalue of A transpose A is nothing but the singular value of A. Therefore, therefore this is equal to sigma max of A. Okay, so you're back to your singular value thing. So singular value decomposition seems to be coming up every now and then, right? It has a very, very major role to play. Now, having said this, so we have the spectral norm of a matrix A. Therefore, the spectral norm of a matrix A is simply the maximum singular value of A. Now, what is of interest is this notion of numerical stability, right? We've been trying to argue as to what will be the change in the solution, relative change in the solution, relative to the change in the observation. Right? So, this relative change. Let's now, in the light of what we know about a matrix spectral norm, let's examine relative change. Suppose we have y is equal to ax, okay, and assume A is invertible, okay, which is the most ideal situation that you can have. If it is not invertible, then anyway, right, we can't do much. But suppose A is invertible, therefore, what do we know? We know that x equal to A inverse x. Okay, we know this. Now, Now let us look at norm of y, that is equal to norm of ax, that is equal to norm of, that is less than or equal to, we know is norm of a into norm of x, right? This is by a definition of norm, right? By that definition of norm, of the matrix norm. Now, or in other words, what we can say is 1 by norm x, 1 by norm x is less than or equal to norm a into 1 by norm y. Now, no, sorry, x equal to a inverse y, okay? This is not x equal to a inverse x, this is x equal to a inverse y. Suppose y is perturbed, right, by a small value, perturbed by delta y. Then because of the fact that a is invertible, right, therefore x gets perturbed by let's say delta x. Or in other words, when y is y plus delta y, x becomes x plus delta x. X plus delta x is equal to a inverse y plus delta y. Or in other words, okay, from this, so it follows that delta x, so it follows that therefore delta x is equal to a inverse delta y. For norm delta x is equal to norm a inverse delta y less than or equal to norm a inverse norm delta y. Let's call this equation 2. Let's call the earlier one equation 1. Okay, multiply 1 and 2. Now, if you multiply 1 and 2, right, because of the fact that every term here is a number greater than or equal to 0, only norms are involved, and therefore, even if you multiply the left and the right hand side quantities, the inequality, right, it does not flip. Therefore, multiplying 1 and 2, we get norm delta x by norm x, because the other one had 1 by norm x here, is less than or equal to, so the sign doesn't change because all are norms here, so therefore this sign won't change. Norm a into norm a inverse into norm delta y, and then there you had actually 1 by norm y, therefore by norm y. Now, if you notice, this is the relative change. It's the relative change in y, and this is the relative change in x, which is the solution. Relative change in solution. Relative change in y or relative change in observation. So what you find is that the relative change in the solution is actually upper bounded by a number times the relative change in observation. Now, it is interesting that norm A into norm A inverse, we know, is greater than or equal to norm A into A inverse, which is equal to norm of I, and the spectral norm of I. Okay. Now at this point of time, right, let us understand that these are all spectral norms. Okay, this is the spectral norms. Okay, these are all two norms of these vectors. Therefore, this is equal to, and because the eigenvalues of the identity matrix are all 1, therefore, its singular value is also 1. Therefore, norm of I is simply 1. Therefore, this number, right, is always this product, right, of these two norms, norm A into norm A inverse, is always a number that is greater than or equal to 1. What this amounts to saying is that this relative change is actually upper bounded by this number times this. Therefore, this number, okay, acts like an amplification factor. Right? The larger this number is, the higher will be the change in the solution for a change in the observation. This is an amplification factor. Okay. And this number is called the condition number. It's called the condition number of A. Called the condition number of A. Or denoted as kappa of A equal to norm A into norm A inverse, which will then be equal to sigma max of A, and norm of A inverse is what? Norm of A inverse is sigma max of A inverse. Just as norm of A was sigma max of A, norm of A inverse is sigma max of A inverse. That is nothing but 1 by sigma min of A. Therefore, this is equal to the ratio of the maximum and minimum singular values of A. Okay? Therefore, this is called so this is the condition number, and this is what will tell you the health of a matrix. Okay, so even if your matrix is invertible, okay, but then if the spread of the singular values is very large, right? So this is like indicative of the spread of the singular values. Therefore, the spread is high. Okay, so then it means that if kappa is high, then A is numerically unstable, is not a dependable matrix, is not really a dependable matrix. That means when you try to take inverse and you want to accept the solution, you may be in trouble, even though it is invertible, even though it may be invertible, even though it is invertible. Okay, if it is not invertible, then of course your condition number will be simply infinity, even though it is invertible. So invertibility by itself is not enough. That is the reason why Hadamard's third condition was kind of very, very relevant. Right, that talked about a continuity of solution with respect to observation, and that's exactly what is captured by the condition number. Let me just take one example, right, with regards to this, and let's take this example that will tell you, okay, what that can help you understand this. Let's take a matrix A, which is 1, 1, 1, 1.0001. Right, so it looks like a contrived matrix. Because it was all 1, 1, 1, 1, then we know that we cannot even invert this guy. But then a small number has been added to the last term just to make it invertible. In the hope that now that we have an invertible matrix, all should be fine. We should be able to use this matrix. But then, as you would expect, that would be a wrong move, because this A, as we can obviously see, if this was 1, then we could not even have inverted it. And all that we have done is, this last number is just a little bit away from 1. And therefore, we expect that this A, cannot be a numerically stable matrix. Now, let's just check this out. Since A is equal to A transpose, okay. So since A is equal to A transpose, okay. Now, first of all, let's just look at the fact that A is equal to A transpose, and its eigenvalues, right? If you look at it, lambda 1. Okay, lambda 1 is approximately 10 power minus 4 by 2. Lambda 2 is approximately 2. Okay, and since A is equal to A transpose, okay, you get the kappa of A, right? If you notice, if you could have remembered, it was root, right? Lambda max of A transpose A by lambda min of A transpose A. Now in this case, because of the fact that A is equal to A transpose, this becomes lambda max of A square by lambda min of A square. That means that is equal to root of lambda square max of A by lambda square min of A. This is equal to lambda max of A by lambda min of A. Okay, this happened because it was a special case of the symmetric matrix. This is equal to 4 into 10 power 4, right? If you divide lambda 1 by lambda 2, lambda 2 by lambda 1. Okay, so the maximum eigenvalue is 2 divided by minimum. Okay, so it is 4 into 10 power 4, which is very large. Okay, therefore numerically unstable. Therefore, numerically unstable matrix. Now, what does that mean? Okay, so if we try to use this for some calculation, we'll go terribly wrong. Say we want to solve Ax equal to B, okay, or Ax equal to Y. Okay, now for the same A, okay, let Y be equal to, suppose somebody gives you Y to be equal to, let's say 2, 2, and let X be equal to some UV. Okay, then if you solve for this, you get U plus V is equal to 2, and U plus 1.0001V is equal to 2. Therefore, it follows that V is equal to 0 and U is equal to 2. Now let's say that my Y changes a little bit to 2 and then 2.0001. Okay, now as we can see that y has hardly changed. Okay, so y has just become y is changed by a very, very small amount, right? Now we would ideally expect our x to not change much, but then then what will happen is x will indeed change. And how does x change? So you get, so if you do ax equal to y for this, you get it again u plus v is equal to 2, but now you'll get u plus 1.0001v is equal to 2.0001. Or in other words, you get v is equal to 1 and u is equal to 1. So therefore, see the change in u and v. Okay, so earlier it was v equal to 0, u is equal to 2, and v is equal to 1, u is equal to 1. So which is a big change, right? And what kind of a relative change have we got here, right? If you want to check that out, what kind of relative change? So if you look at delta x now, what is the change in? Okay, let's first look at delta y. What was the change in delta y? So delta y changed as 0 and minus 0.0001. What is the change in delta x? Delta x changed as minus 1, 1, right? Because 0 became 1, 2 became 0 became 1, and 2 became 1. Therefore, norm delta y is equal to 10 power minus 4. Okay, norm delta x is equal to root 2. What was norm x? Right, norm x was, so x was 0, 2, so therefore norm x equal to 2. And what was norm y? Norm y is root of 4 plus 4, 8. That is equal to 2 root 2. Okay, therefore, according to our expression, right, that we had here, which was this inequality, right? So norm delta x by norm x, if you see, so norm delta x is root 2 by norm x, which is 2. It is equal to 1 by root 2, should be less than or equal to the amplification factor kappa. Kappa of a was 4 into 10 power 4 into norm, what was that? Norm delta y by norm y. Correct? Norm delta y by norm y. So norm delta y is 10 power minus 4 by norm y is 2 root 2. Right? Therefore, this number is equal to root 2. Okay, whereas the one on the left is 1 by root 2. Therefore, clearly 1 by root 2 is less than or equal to root 2. So it does satisfy this inequality. But then what you also notice is that, right, the role of the condition number is such that if kappa is small, right, as kappa becomes low, of course you can only have a minimum value of 1. But as kappa increases, then kappa decreases, it automatically makes sure that this relative change will always be less than or equal to, so the upper bound will automatically reduce, right? Therefore, that is the reason why having a kappa that is close to 1 is most ideal. And right, I don't think that it's only identity matrix. For example, here, right, we had an identity matrix that had a condition number. Right? Clearly the identity matrix has a condition number that is 1. But then there are in fact other matrices that also have a condition number that is 1. For example, unitary guys. If you take a unitary matrix, right, because of the fact that u transpose u is equal to identity, therefore it has a kappa of u is in fact 1. Okay, so therefore it's not true that only the identity matrix will have a condition number is 1. There are in fact other matrices also that can have 1 as a condition number, and that would be the most ideal matrix to deal with. But then even a higher number of condition number is acceptable, provided that it's not way too large. Okay, if it becomes way too large, then it means that your solution becomes very sensitive to your observation, to any change in observation. Therefore, even if you have a matrix that is invertible, it will not help you because your condition number will be really high.